I work at Bloomberg. I'm the software engineering manager for the code governance team. Our team does the static analysis and automated refactoring like at scale at Bloomberg. And we also work to build consensus on engineering practices across the organization. So a little bit about me. I've been working for 20 plus years in and around build systems, package managers. I was a Debian maintainer, Debian developer for a while. I introduced the package manager that has been used for the past 10 years at Bloomberg. More than 10,000 C++ projects are in that package manager. And as I said, I'm now working more in static analysis and building consensus. But also in the last 2 years, I started getting more involved into the SG15, the tooling study group in WG21, to help figure out how can we make C++ modules work. So I'm going to work a little bit, like very briefly, on the background of where we are with modules, where we were with modules. Then I'm going to focus. Honestly, it's kind of like half of the talk because I can't really talk about header units without explaining how complicated named modules are for the build system. And then finally, I'm going to dive into the really important challenges that we have in implementing header units. And finally, I'm going to be a little bold and try to suggest a few things that we could do and what my personal take on that. So when modules was standardized in C++20, but it was not exactly without controversy. There was a lot of feedback from the build system side that there were various challenges for the implementation of modules. There's this miscommunication that happens that folks still have the expectation that in a world with C++ modules, just invoking the compiler by hand is going to be a reasonable teaching workflow. That's not true. That just using a plain make file is going to be a reasonable starting point for C++ projects. That's not true. Like, all of that changed. But a lot of the work that happened between 2020 and 2021 on the tooling side was mostly focused in what I'm going to call like highly regulated environments, which can also be called monorepos. And what I mean by highly regulated environments is an environment where the entire chain of dependencies is controlled in a precise way, and where you can be fairly confident that you understand how many parses of a given file you're going to see in that build environment. This is not true for Bloomberg. Bloomberg has a very open-ended package management system. We, in fact, use the Debian packaging format, which means we have a source package, we build that source package, which produces binary packages, and then you can use those binary packages as build dependencies for other source packages. Meaning each build system has complete autonomy, each project has complete autonomy on how the build system is driven, how the build system is configured. The only thing that they're held to is some coherence on the ABI level. And if you're curious about more details on that, me and Brad gave a presentation on that in CppCon 2021 that talks a little bit about that experience of driving like 10,000 packages at Bloomberg. But the really important part is the way that we do package management is exactly the same way that Debian does package management, same way that Red Hat does package management. So the challenges that we would have in adopting modules would be the same challenges that Debian would have in adopting modules, and that Red Hat would have in adopting modules, that Conan builds would have in adopting modules, that VC package builds would have in adopting modules. And so that's where we kind of said, I think we have to step up and start working more closely with the standard committee to make sure that we don't get at the point where the C++ ecosystem fractures between C++ that works in monorepos and everyone else. And so that has been the focus. And this was the paper that I presented initially, like trying to present where these distinctions actually break down on the implementation of modules. So in the past 2 years, like we have been working like consistently through a lot of those challenges. Bloomberg has been working and funding work with Kitware. CMake has now experimental support for modules. Bill here is going to talk more tomorrow about where we are and where we're going on CMake for the module support. But there's still significant work to be done for named modules to be usable in production environments. My hope with the work that we're doing with Kitware is that by the end of the year, it should be possible for you to build a project where you use modules internally to that project in a production environment using CMake. Right, Bill? He says yes. Header units, on the other hand, we don't have a coherent plan at all. Like for named modules, like we know what needs to happen for us to be able to use named modules in like this open-ended environments like Bloomberg, like Debian, like Red Hat. But for header units, we don't have a plan at all. We made very little progress in the past several months, and I've been trying. There was an interesting anecdote in Kona where we had this whole afternoon like discussing header units, and at the end of the meeting, I literally just say, forget about it, like nothing that I said works, let's just go home. Hence this talk. So before I talk about header units, and unfortunately, like this is kind of like half the talk, I have to explain how named modules work. And again, I'm not going to talk about the language, I'm talking about from the build system perspective, what needs to happen for modules to work. There are several types of translation units that were introduced by modules, and the name of those types has been one of the things that we settled over the past 2 years. The first one is what we call the primary module interface unit. The primary module interface unit is the one that you think about when you import a module. When you're outside of a module, that's the one you see directly, right? So you can identify that by the first line. There's only one translation unit to have that first line. Export module dent, in this case. And that is the primary interface unit. And you control what's visible or not via the export keyword. In this case, we're exporting those two functions, one with the definition embedded in the interface file, one without. Unlike with headers, that definition actually does not end inlined. It actually goes into the definition file. You have like two different processes that end up being in the same compilation, in the same compile invocation most of the time, but you actually end up with a BMI, a built module interface file being produced alongside the object file. So the declarations would go into the BMI, and the definitions would go into the .o. Sounds good. Now, we don't have to put the entire module interface into the primary module interface unit. We can break it down into parts. And those are the module interface partition units. And you identify it by the presence of the export keyword and the presence of a module partition in the module name. That means that this translation unit contributes to the visible interface, to the external interface of the module. So now I'm saying that these two other functions are also part of the module interface. And as with before, you have these two different processes that usually happen in the same compile invocation, one producing the BMI and one producing the object. The definitions go in the object, the declarations go in the BMI. But any module interface partition has to be re-exported by the primary interface, meaning line, well, it's miscounted, that's great. So line 2 that's not supposed to be true, that's not supposed to be 3, says export, import, dent, towel. Like that is a requirement. Anytime that you have interface partitions, they have to be export imported in the primary interface. The change, though, is that from the build system perspective, you now need to translate the BMI for the module partition being imported before we can translate this translation unit. So that means we don't have parallel builds in C++ anymore. we have topologically sorted builds. The other type of translation unit is what's called, and again, this was a very contentious thing to find a name for, internal module partition unit. And you identify that because it has a module partition, but it does not have the export keyword. That means that this does not contribute to the external interface of the module, meaning there can't be any export clauses in this file. There is two possibilities. This internal partition can be reachable by interface modules, or it may not be reachable by interface modules. So if it's not reachable by the interface modules, when would you use it? And the answer is in the module implementation unit. The module implementation unit is the one that you identify by having module, the name of the module, without the export keyword. And this is the only type that you can have many translation units with the same module declaration. Those do not contribute to the module interface. And if we look at the diagram over there, you can see that it does not produce a BMI. So the three first types, they are what we call importable units because they produce BMIs. And the module implementation unit is not an importable unit. It only produces an object. And as I said, you can have two of them. And as before, the compilation process depends on the BMI for all the things that are imported. And as the slide says, when you're in the module implementation unit, the interface unit is implicitly imported. All right, so let's look at how this looks in the end for the entire build system. So we start with the primary module interface. We want to produce an object file and a BMI for it. But it depends on the BMI for the partition, the interface partition. So we need to do that first, and then we can produce the object for it. But then we have an implementation unit that produces only a .o, but that depends on both the module, the primary interface BMI, and on the internal partition that it's importing. And that comes from a different file that also produces an object. And the same thing with a different module implementation unit. And then all of the objects get linked into the final program. Make sense so far? So let's think a little bit about the steps of the build process to get there. Because I explained the end result, but I didn't explain how the build system decides that this is the end result. So there's two important things that happen first. You need to identify the external importable units. You need to identify external header units. Sorry, identify header units. And I'm not going to talk about header units right now because I want to leave that for the second section. Then after you identify the external module units, importable units, you can perform the dependency scanning. After you perform the dependency scanning, you have a build graph that will happen topologically sorted. And finally, you can compile the objects and generate BMIs, and finally link the final program. So why I'm calling out external importable units? Because your build system needs to know what it can import that is outside of the current project. Let's say you have your local CMake application, and let's say you want to import a boost module when those exist. The boost module is not necessarily going to be inside of your CMake project because, again, I'm talking about this open-ended environments where boost is going to be available as a pre-built artifact for you. So how do you know which modules exist for you to depend on? How do I know if any existing BMI can be reused? And if a BMI cannot be reused, how do I produce my own? And this is where we hit like the first big snag, because the ecosystem is fragmented enough that we have 0 starting points for interoperation between package managers and build systems to make that discovery. Like there's literally nothing. Like if you have a CMake project and you're trying to consume a library from a build-to project that was not particularly made available to CMake, like there is no way to know what are the modules that that library provides. So the expedient consensus we got, and I say expedient because the real answer is package management, and your package manager should be able to answer the question, sorry, your build system should be able to ask your package manager for the packages that I depend on, which modules are provided by which. But that's not a thing right now. So the alternative, like expedient alternative that we have so far is, let's use the link line, right? Like at some point the build system needs to find a link line for the libraries. So let's just co-locate a metadata file alongside the .a or .so and have the logic of finding that .a also be used to find the .so, to find the metadata files. And that would say, what are the modules that are provided by this library? What are the source files for the interface units, or even any reachable internal partition that will need to be translated when producing a BMI? And also, how do I parse that module? Because that module may have a dependency on a header that I don't know where it is, because it's going to be an entirely separate translation. So
like if you said like I want to link with like foo or something, it would go look for libfoo.a or libfoo.so, and then it would also look in those same search directories for, can I find this metadata file that tells me what modules are exported by libfoo?
Correct. And that was the two papers that I'm linking there. Like it was the process of getting to that consensus. So now I need to enter like a little sidebar of why do I need to produce my own BMI? Like we reuse objects all the time. Why is BMI different? So the answer is probably comes from the origin of the implementation of importable units. Because both in GCC and Clang, this comes from the history of precompiled headers, and it evolved from there. And there is a lot of assumptions, like actually like, can I mem copy these things from the BMI into the running process? Can I just mem map this BMI and read the AST from it? Which means that the BMI is a lot more sensitive than the object file. So we have this new concept of BMI compatibility beyond ABI compatibility. Like in the example that I gave, we have a bunch of objects linking together, right? So they have to be ABI compatible, but each one of those compilations also had to import a BMI. And this interface is new. Like this binary interface is new, and it represents a new type of compatibility. So while you can link multiple objects from different compilers, you cannot import a BMI produced by one compiler in another compiler. So if you have a BMI that was produced by GCC, and you're trying to import that from Clang, it's just going to fail at compile time saying, I don't know how to import this module. So how did this look like? So let's imagine the situation we had before. So let's imagine that we have the interface partition producing like a GCM, which would be like the GCC module format, and then a dent.ixx generating the dent.gcm. Again, we have the dependency because the interface partition, the primary interface must import the interface partition. And now I have an other project somewhere else with other.cpp trying to import the dent module from dent.gcm. Like this is literally just fail at compile time, and that's it. No recourse. What the build system needs to do instead is to say, oh, because of the topological sort, I need to go find denttal.ixx, produce dental.pcm. Let's say this is Clang, and PCM is the extension that Clang is using, because not even extensions we can homogenize. And then after I produce that, I can go get dent.ixx, produce dent.pcm, and finally use that to produce my object. But this has a very important consequence that is really, really, really important to keep in mind. Because while we link all the objects together, and like the BMI is not an argument to the linker, we do end up in a situation where the same module is translated more than once. It contributes to different objects, and those objects contribute to the same program. And that has to be OK. That is necessary for modules to work. So again, this is the story about difference between BMI compatibility and ABI compatibility. So this is not necessarily an ODR violation, because you could produce ODR equivalent BMIs and have them contribute to different objects and link them together, and that's all fine, that's all working as intended. All right, so now that I accept that I need to produce different BMIs, and before I go there, I just want to highlight one thing. I'm using the example of like Clang and GCC, but I really don't want you to be hung up on that, because if you use different versions of the compiler, it's not going to be compatible. If you use one argument or another, it's not going to be compatible. If you have different versions of the standard, it's not going to be compatible. So even though libstandard C++ is perfectly fine with you building different objects with different versions of the standard and linking them together, you will not be able to use a BMI produced for C++20 and a BMI produced in a translation unit that is being compiled with C++23. So you will have to produce a different BMI in that case. And again, it's not necessarily an ODR violation. It may be even a benign ODR violation in some cases, because that's a thing. And that's all fine, and that's all working as intended. And finally, even on the same version, even on the same language version, different versions that control the behavior of the compiler may also cause you to generate incompatible BMI. So I'm going to go back to that a little bit. Like, I think I went a bit off the order. I'll go back to the order that I had. So now that I know that I need to produce BMI and that I can have multiple BMIs in the same final program, contributing to the same final program, how do I know how to produce it? So if, again, I'm talking about an open-ended environment where I'm consuming a pre-built artifact of a library that was produced by a different build system into my own build system. So I don't know how that library was compiled. My interface to that library is a bunch of files on disk. Even if I did know, it may have been a different compiler, it may have been a bunch of other things. And even if it was everything the same, I could end up producing an incompatible BMI because of those different flags. So that's the other step that we had to take. So we had to introduce this new concept of local preprocessor arguments. It's really hard to name things, and this is not a good name, but it was the best one that I could find. So essentially, and I think the example is probably the most useful thing. Let's say you have two source files, right? And one is compiled in one BMI way, the other is compiled in the other BMI way. And you need to produce the BMI for the first. But other.cpp imports dent. The compile command for other.cpp includes -i/some other -d option for other equals 1. We really, really, really don't want those preprocessor arguments to leak into the translation of the module interface unit, right? Like, we want to keep that separation. At the same time, when the module was produced, there were some flags that are necessary for parsing that particular translation unit. In this case, let's say -i path to some header, -d option for some header equals 1. And those we do need when translating my own BMI for that same module, because I don't have that path in my compile command, and I don't have that -d, so I would be translating that interface unit incorrectly. So, and again, this is one other step that we got consensus after much effort. And so the process by which you compose the compile command for producing your own BMI is you start from the command line of the translation unit doing the import. You remove the local preprocessor arguments of that translation unit, and then you add the local preprocessor arguments of the translation of the module that you're importing. And that's how you compose the command line for the BMI that you need to import. All this before the dependency scanning starts. So at this point, we're only talking about metadata. The module metadata has to say what are the local preprocessor arguments, what is the source file for those modules. Build system needs to know what is the local preprocessor arguments for the local files, what are the local files, and all of this before we even read any source file, which is a good segue into dependency scanning. I was a little bit disappointed when I understood this because I was hoping it would be simpler, but you do need a preprocessor to do the dependency scanning. You can have import macro. There is a relief where you can't have the import keyword be a macro, nor the module keyword be a macro, which means that you can have a preprocessor that lazily evaluates macros only to the extent that's necessary to perform the dependency scanning. So it's some relief. It would have been much nicer if this happened like in a preamble before any preprocessor shenanigans could happen. And you need to do this on every source file. And I hope some of you got this, but it's not just your source files. You need to do that in all your source files and all the source files of all the modules provided by all the libraries that are in the context of your build system. Because you don't know which libraries provide which modules. You don't know which modules depend on which modules. You just know that those are the modules, those are the source files, and you need to find the dependencies. I'm going to punt on header units on purpose.
Not the header units, the headers, the graphic words.
Yeah, header, sorry, yes. And you can have an import inside of an include, and you can have an import inside an ifdef. I'm going to go that in more details, but yeah, it needs to be a full preprocessor to do dependency scanning, even though it can lazily evaluate only the things that are needed for the dependency scanning.
Does this mean that you need to have the source, at least the header source in your packages, like invariably, like there's no separation between dev packages and regular packages?
So you have a distinction based on the translation unit types that I mentioned at the beginning. You don't need to include your implementation units, and you don't need to include your internal partitions if they are not reachable by the interface of the module. But everything that is reachable from the primary interface unit has to be available as source in your devel package. Like if you're thinking like Debian, like lib boost file system -dev will need to deploy those sources alongside the .a. Like in a world where there's no headers anymore, let's say. The header, the sources for the interface units and everything reachable from it have to be published with the binaries. Of course, the dependency scanning also needs to be rerun if the arguments change. And I'm going to get into a bit more details of how that gets even more fragile. But again, it also depends on resolving the compiler commands, not for my own project sources, but I also need the compile commands for all the modules external to my project that I may import. So there is a benefit. Modules don't change preprocessor state, thank God. So the scan is a single pass. Like it is entirely possible to do one translation unit at a time, completely in parallel to do the dependency scanning, and and form the entire build graph at the end of this process. And we have a de facto standard. I'm saying de facto standard because I can't say standard if we're only putting things into the modules ecosystem TR, so I guess de facto. But all compilers right now support the dependency scanning outputting in a single format, so progress. Again, all compile commands need to be known ahead of time, but the build graph is complete and stable after the dependency scanning. Files change need to be rescanned, and which can adjust the dependency graph, right? Because the name of the file has no bearing on anything. So you can say file butterfly.ixx, the extension of the different types of translation units is still in flux. If you have butterfly.ixx, there is no requirement in any form that module will provide module butterfly. So the only way to know which modules are provided by what is by actually reading the files.
But please, like, just do the normal thing that everyone expects.
Yes. It's the thing about like the standard doesn't really acknowledge that the source is in files, so it can't say anything about the names of the files. Yeah. Right, so what about the incompatible BMIs I was talking about? So the compiler is the only one that knows. Like, it is absolutely unfair to ask poor Bill and Ben to try to like understand Clang arguments and GCC arguments and MSVC arguments to figure out if this is going to be compatible or not, right? Again, we're not talking ABI, we're talking BMI. So the build system needs to defer that logic to the compiler, right? In the worst case scenario, we need to build all BMIs for all translation units, right? In the worst case scenario, it's the worst performance possible. So this is currently implemented in CMake, not the worst case scenario. So in CMake right now, the module unit it belongs to the target declaring that module. And then we just assume that the BMI is going to be compatible, which is mostly fine, and that's the plan for this year. That's the thing that we're going to be able to do at the end of this year. If you have a reasonable CMake project where you don't have like half of your targets in C++20 and half of your targets in 23, you're very likely to be able to use modules by the end of this year. Otherwise, it's just going to be a compiler error saying, can't use this BMI. And there's not going to be much help explaining why. It's just, can't do it. So what do we want instead? I'm doing time like exactly on point. We want the BMI that is required by a translation unit doing an import recursively to be owned by the translation unit doing the import, which is the worst case scenario, right? Like every translation unit produces all BMIs it needs. But we need to deduplicate the work when possible, right? If we have a coherent build system, let's say everything is ABI coherent, and I'm not going to talk about benign ODR violations. If everything is coherent on an ABI level, the fact that you're using BMI incompatible flags should not be a user error. The build system should instead resolve that for the user. And this is a point that is particularly important for Bloomberg, for instance, and probably very important for Linux distributions. A library devel package should be able to ship a BMI that can be used in the cases where it can be used, right? For instance, in Bloomberg, we have a fairly well-controlled, like 80% normal case. So for those 80%, we should be able to just ship a BMI and have the other build system recognize that BMI and move forward without having to build that BMI itself. So where we are is the compiler should offer a compiler option smoke signal, anything, where you can ask, give me an identifier, an opaque token that tells me what is the compatibility of this BMI, right? In the case of Clang, we're pretty sure that's literally going to be a hash of like internal properties of the compiler, relevant flags in the command line, and discarding flags that are not going to affect the BMI. We just discussed yesterday that because the compilers don't support this yet, CMake will do a pessimization of just doing a checksum of the baseline command without the local preprocessor arguments, and use that as the identifier. Because if the compile command is the same, like it most definitely is compatible. But again, no compiler supports this yet. We have a pessimization plan, and we have a plan for how to make this a bit better. So how do we tell the compiler which modules do we need, right? Because we did the dependency scanning, but there is no mapping of names. There is no lookup mechanism. Like I can't expect like an include statement that I'm going to traverse a path and find the BMI, right? That was actually my first proposal that was very violently disagreed with. My first proposal was let's just do the normal thing and just put the BMIs and the sources in a directory named after the modules, and the compiler can figure it out. That was not. Let's just say that people were not a fan. So the module mapper, that is the way that you tell the compiler what are all the modules that the compiler needs to know about for this translation unit, has been, like, from the very beginning, one of the very contentious topics. One of the early proposals has been that you just have like a network protocol between the build system and the compiler, and then the compiler just orchestrates the build of the dependent modules, and the build system figures it out, and it just happens. However, in an environment like ours, where we're transitioning to remote execution, this is dead on arrival. Like for us, this is absolutely inviable. We need all the inputs to the compiler to be known before the invocation of the compiler. So the alternative then is to produce a static file that says, in the case of GCC, you have to say module A comes from this BMI, module B comes from this BMI. In Clang, I think you just give a list of all the BMIs to read, and it just reads them all. But again, going back to the inputs to the compiler, the naive version would be, all right, I'll just give a list of all the modules to all the compile commands, and it should work. And it should. But if you overspecify, it means that you're invalidating every translation unit whenever any BMI changes. So that's not good. So the solution is to have the build system generate a per translation unit module map containing only the BMIs that that particular translation unit needs. And this is fine because, again, the dependency scanning had this information, so we know how to do this. So how does this look like in the end? So we start with each source file in the project. We have to identify the local preprocessor arguments for each of the translation units in my project. Generate the baseline compile command, the one without the local preprocessor arguments, for each one of those. Deduplicate that and generate the compiler, the compatibility identifier for the BMI, and deduplicate that. So we have a set of flavors of BMIs that we may need in this project. Now, for each one of those identifiers, then for each translation unit, it includes like the ones in my project and the source files for the modules that I'm importing from outside of the project. I need to append the local preprocessor arguments for that translation unit, do the dependency scan, identify the outputs and inputs for the translation unit, generate the input module map, and finally generate the final command with pointing to the module map. So at this point, you have a complete build plan You have a complete graph. If you use Ninja, you can just say like Ninja, and it goes. It will go as fast as it can, which is not going to be embarrassingly parallel. It's going to be topologically sorted. But we should be able to only build the things we need, right? The graph, of course, looks like objects can depend on BMIs. BMIs can depend on BMIs. Thinking about changes again. A change may introduce a new module, may remove a module, may add a new dependency, remove a dependency, and change the compatibility identifier of the BMI. The last one means that we need to do a full dependency scanning again. Because in a different compatibility mode, there may be an if-def that changes a module from one file to another. And so we have to do the dependency scan for every flavor of BMI that the build system needs to do. So how do we make this graph work? And how do we make it work in a way where we don't have like lots of synchronization points during the configuration time that will cause the configuration time to become bottleneck? The trick is to, like, if we're talking about like make targets or Ninja targets, we use the compatibility identifier in the name of the BMI file. Then we use the name of the module for the output of the BMI, because that reduces the number of times like that we need to synchronize global information. So how does that look like? So we start with, let me start from the end. So we have the object in order, and the BMI. In order to produce the BMI, we know that we need a module map. In order to produce the module map, we need to know the output of the dependency scan, which depends on the command line and on the source file. But we also need to know what is the compatibility identifier for the BMI in this particular context, which depends on the baseline command, which depends on the distinction between the local preprocessor arguments and the actual command line of the compiler for that particular translation unit. So let's say that the identifier in that case is deadbeef. So we put deadbeef/dent.gcm in the name of the output file for this translation. And because this is the primary module interface that depends on the interface partition, we say that those two depend on deadbeef/dental.gcm, but we don't have to care where this comes from, right? We can say, here's an unbounded edge in my graph. At some point that's going to be sorted out. I don't have to care right now. Make sense? Now, let's see that I have like other.o, which is produced from other.cpp, so I do the same thing. But now I have a different compatibility identifier, let's say beefdead. Now, my dependency will say beefdead/ident.pcm, right? Again, I'm scanning this one, completely standalone, can be even in parallel with the other one, and it's all fine. I'm leaving an unbounded edge in the graph. At the end, it's all going to be resolved. But because I have both deadbeef and beefdead as compatibility identifiers, I know that I also need to do the scan and build a plan for beefdead/dental.pcm, right? Because I need to produce beefdead/dent.pcm. That is the primary interface unit for the module dent in the context of this particular translation unit with the compatibility of beefdead. So again, I go to the module map that depends on the compatibility identifier to know what the name of the module file is going to be, which again depends on the compile command line and the distinction between local and preprocessor arguments, same way as before, right? The important point here is all of this happens in a single pass, one per translation unit, completely in parallel. We just join the entire graph in the end to build the plan. All right, questions so far?
Do you think that, so it sounds like at the moment right now, around the fact that we have all of these BMI compatibility issues, it largely just comes down to the fact that this is kind of like we're getting to the point here where modules are implementable, but it's not all yet standardized. Do you think that that is something that we eventually, at some point in the future, can tackle to make some of the rest of this less necessary? Or
Theoretically, yes. Do I think that the Clang and GCC developers have an interest in like making BMI compatibles? I haven't seen any signal in that respect. Because again, how the optimization here is to have a BMI that is the most efficient to be read by that particular compile, right? And if you think about it, you're going to be compiling your own code a lot more frequently than the BMIs that this code is important, right? So you do want the import to be as efficient as possible. So Gabriel dos Reis has the IFC format that he has been pushing for. He has been advocating that this should become like the standard BMI format. And I think it's a very laudable initiative, but in reality, the efficiency goal of making the import as fast as possible, I think will always take precedence.
Could it be that you do both, right? I mean, a lot of places when these things come up, you just put both formats into a single file. You can just provide that with portable form and non-portable form. Everybody can agree to fall back to the portable form if they don't.
Yeah, so the paper that introduces the idea of the compatibility identifier like has a provision for if your compiler knows how to read more than one file, just return all of the identifiers that you can read. Like the first line is the one that you're going to produce, but like this is all that you can read. And the idea is that like maybe if Clang learns how to import IFC, then it would just return that additional line, and the build system would know that it could deduplicate more doing that. There was another one.
So I'm thinking about like I want to package a library that I then give to someone else, right? So with include files, I would just have like one like include directory, and I put like all kinds of files in there, and then like whichever files are included by name, right? It will just pick them out of them and leave the rest alone. With the module interface files, I have the problem that I cannot tell from the file name which of the sources that are in this directory need to be taken into account for the dependency analysis. So how does this work? Like, do I also need to ship to the build system like a list of what are the actual sources?
Correct. And this is the point that this no. No.
Sorry.
That this two papers introduced. So ideally, the package manager would have that list, and the build system would ask, and the metadata would be transmitted from the package manager to the build system. Because we don't have that interoperability now, we're going to use the location of the archive or the shared object to find a metadata file that have that description. So when you're producing a binary package, you're going to essentially install that additional metadata file alongside your library object. And that's how the build system can find out which source files to care about.
What about module only then?
So interface unit only module libraries. We don't have a good answer except ship an empty archive anyway.
Can you just quickly reiterate when and why we do the stripping of local preprocessor arguments, and when we do put them back in, which one we're putting back in?
So this is a very important and difficult distinction. There is no mechanical way for us to know if an argument is a local preprocessor argument or not, right? In the case of libstandard C++, you have -d cxx c11 API equals 1 or 0, right? It's a preprocessor argument. But if you put it in the local preprocessor arguments, you're going to be generating incompatible, like API incompatible things. So that definitely does not belong there. But in this example, I have like the path to a header that's used by the interface unit, and an option for that header that's not needed by anyone importing the module, right? The module encapsulates all of that. And so that's a local preprocessor argument. the end result of all those things is that this is fundamentally altered information. The author of the module will have to decide what are the things that are required for my translation unit, but that should not leak to the translation units doing import of my module. And the same way, when I'm a translation unit that imports a module, I need to decide what are the preprocessor arguments that shouldn't leak to the interface units that I'm importing. All right. Any other question? All right. So again, I hope I answered why you can't just use make anymore. And I hope you have like a bit of a picture of why it's taking so long to get modules. But we're hopeful. Like we're getting there. Now header units, on the other hand, that's a very different beast. First challenge is preprocessor state. So if we look at like a normal source inclusion, when the compiler is going through the preprocessor run, the state of the preprocessor is entirely unambiguous. It starts at one point, and it processes like one directive at a time. Like it does the define dent, and then you do include bar, and then the other header, if def dent, like you know that dent is defined, you know that bar value is going to be 42, and it's all good, right? In header imports, that's a different story, right? Because the header unit is not supposed to be contaminated by the preprocessor state of the thing doing the import. Is that distinction clear? Right. So dent may or may not be defined, right? It depends on the command line for the translation unit of the header unit. Okay, so I just need to translate the header units first, right? Easy enough. But let's like, I don't know if it's obvious, but I'm using like the vertical alignment to say which file is being included. So like the include bar.h is like the second file, and then one bar and two other bar, right? So when you're doing define dent, import bar, if def dent, define bar value, one bar, and then later you do import bar value. Now, what is your dependencies graph? Right? You need to know, like, you need to know that before you can do the dependency scanning. Like, you need to know the dependency before you do the dependency scanning. So the compiler, like, the dependency scanning has to emulate the import behavior, right? So the compiler, the dependency scanner is going to have to essentially, when it sees import header, like push the state of the preprocessor away, start a new one, read the imported header, and then pop that state and merge the preprocessor state from the header unit into my preprocessor state before continuing. And again, at the dependency scanning step. But where does dent come from anyway? Right? Like it comes from the command line of the header unit translation. So this is fundamentally different from named modules. Because with named modules, we could analyze each node in the graph independently, leaving like the unresolved nodes to be found at the end of the process. But here, we depend on the command line of the header units that you're going to be reading in order to do the dependency scanning, right? So if we look at the graph again, what ends up happening is like bar.h local preprocessor arguments become a dependency of the dependency scanning. Sounds reasonable enough, but this is before the dependency scanning. So how do I know that I need bar.h before I do the dependency scanning? Well, the answer is like you don't. You really don't.
Or have a lot of
If you have a monorepo with the entire world, you can specify it, yes. But in open-ended environments, that's not really an option. So this is the moment in the Kona meeting where I just said, none of this works. Forget everything I said. Because what ends up happening is the list of header units and the local preprocessor argument of every header unit in your project and that you depend on become a dependency for the dependency scanning of the entire set of sources. So this creates like a huge bottleneck in the dependency chain. Some build systems may be able to say, fine, I'll do the dependency scanning again. It produced the same result. I'll stop and not do anything more. Like make does not. Like if you invalidate a target, every other target's going to be rebuilt. I don't know if Ninja knows how to do that. I think it doesn't. I think Ninja will also just keep going because you invalidated a target and every dependent target's going to be redone. It gets worse, of course. So the standard also allows an include to be transparently replaced by an import. This has a very important side effect, like for header units to be saner. Because if you have an include and an import of the same header, like what does it mean? So the compiler is free to say like, you know what, you said include, but I'm just going to import anyway. But if you had a header unit, if you had a header that was not a header unit and it becomes a header unit, the addition of a new header unit that nobody uses also changes the dependency scanning for everyone, because now you need to make sure that you don't need that BMI anywhere. So that was the first challenge. The second challenge is the identity of the header unit. So, and this has been a problem in headers forever. And we have kind of just accepted that include guards are what you do. Or if your environment is moderately sane, Pragma once may work for you. But this complication is why Pragma once never got standardized. Because knowing like what is the identity of a header, like what is the identity of a source file being included, is actually really, really hard. There is no convention right now, even in the early support for header units, to make sure that the thing that you're seeing in an include and the thing that you're seeing in an import actually are the same file, right? Because we're giving the list of BMI inputs to the compiler. And so if my include path would find this header here, but my build system produced the BMI from this other file, there's nothing to prevent that from happening. So again, adding a new header unit may completely change the meaning of your program.
There's a lot of things named config.h.
Right. And this will, like, I cannot see how this will not become like a major source of confusion for developers in large code bases. What do you expect? Like, I honestly don't know what the behavior should be, right? Like you have two includes and an import, and they're all the same thing in the end. Like, what does that mean? I don't know. Like, I think source inclusion using include guards is the only way to make it the same, and it's the best we can do, and we should just accept that. I want you to think a little bit about, like, if the compiler does not replace the include by an import, what actually happens if you do an include and then you do an import, right? Because the imported header unit is not going to be eliminated by the include guard because the preprocessor state doesn't affect the imported header unit. So you will end up with like all the declarations at once, twice, I guess. All right, Third point, misleading performance costs. So one thing that is like becoming clear is that the pruning of unreachable entities in the BMI is going to be fundamental for us to get the promised performance characteristics of the module systems, right? When you have a module, like you're going to have a bunch of code and you're going to have a bunch of exported things, but like the code inside of the definition of an exported function does not actually need to be in the BMI. And so for the performance characteristic that we're expecting, we're eventually going to need to prune that declaration, that definition from the BMI. With header units, there's nothing to be pruned. The entire thing is exported, right? So that by itself is already a problem. But it gets worse, and this is something Cameron DeCameron, he said it. There's going to be a blog post from Microsoft about this in some point in the near future. One thing that they're learning is if you start the adoption of header units in the middle, and you end up with header units that include the same non-header unit headers, the performance actually gets significantly worse. So it's very misleading. You need, like, for header units to be useful, you have to adopt from the bottom up. And you have to rely on like the hash include to import transparent translation by the compiler. And then you can get the benefits. Any questions so far before I? All right. So how much support we have for header units? The answer right now is very little. Like in GCC, for instance, if you try to do dependency scanning of a file that imports a module, it will stop the dependency scanning saying that it needs the BMI for the header unit in order to do the dependency scanning. Because after all, it needs the preprocessor state. So it doesn't have that emulation step that I mentioned. GCC and Clang, like Clang has some support because of header units. But again, it has the relationship with the dependency scanning is still not sorted out. It also does not have this emulation step in the dependency scanning that I talked about. MSVC has some support, better than GCC and Clang right now. But again, it also does not have this emulation, so it's not implementing the correct semantics of header modules. And no open source build system, like as far as I know, at all, supports header units. I get this question a lot, like people think, isn't this the same as precompiled headers? And like, it looks like it, but all the restrictions that make precompiled headers work were removed in imported headers, right? Precompiled headers work in a very narrow scenario. Like you have to comply with very specific requirements precompiled headers work. You have to comply with very specific requirements in order for precompiled headers to work. That's not true with header units. So it's also not the same as Clang header modules. And Clang header modules does have a relative adoption. But there's two modes of Clang header modules. There's one mode which is the implicit mode, where the compiler figures it out and goes generate the BMIs as it's needed, which again does not work for a remote execution where we need to know all the inputs to the compiler ahead of time. And explicit header modules, which require like all the declaration to be done up front, we have significant reports of success in like highly regulated environments, i.e. monorepos. But we have very good reasons to believe it cannot really be successful in open-ended environments. Because having like different header units that were parsed differently that end up including a third header module, like this fails really quickly. So it needs like a fully regulated environment where you have one parsing of each header module and that's it. There's no diamond problem with different parsings. Is it possible to make it work? And yes, there are two things that we can do to make header units work. The first is removing the need for the compiler to know the compiler arguments for the importable headers. And we could achieve that by requiring a metadata file alongside the header that describes that. Right? So the compiler would be able to find the header, see, oh, is this a header unit? Let me look at the metadata, let me do the dependency scanning emulation thingy, and I will be able to do that. But we would also need to remove the implicit conversion from hash include to import, because otherwise we still need to give the complete list of header units up front, which is also like a huge a huge dependency graph bottleneck that really does not work well for open-ended environments. But if we require changes of existing libraries in order for those libraries' headers to be used as header units, we kind of defeated the point. Because the point of header units was as like a transition mechanism for the libraries that already exist, the headers that already exist, so I could just import those and move on with my life. And so I don't know how to answer to that point. And the second thing is the emulation of this preprocessor stack of the compiler having to like start a new preprocessor state, push it aside, do the thing, merge back, and keep doing that recursively for every header unit. We don't know what the performance characteristics of that is. It could actually perform really, really poorly because you're like restarting the preprocessor state every time. If you're including the same headers more than once, you're not going to be able to do, well, if you include the same header before and after jumping jumping down the stack, the include guards are not there, so you're going to have to read the same file again, so the include guard optimization goes away. So we don't actually know what the performance characteristics of that emulation is going to be. And finally, like when I had like the diagram showing like the different preprocessor state where like we don't know what dent is going to be, and it depends on the state of on the arguments of the compile command line for the other translation unit, and you need to like create a new thing, push it down. Like, sure, the computer can do this like reasonably well, even if we don't know the performance characteristics. But I really want to know who's like looking forward to teaching people how to know what your preprocessor state is at any given point. Now that you have to explain that you need to, oh, an import header, cool. Hold that thought. Let's start over. Let's look at what compile command for that header unit is. Let's like try to trace it down. Oh, hold that thought, push it down. Let's look at the other one. Like I really don't want to be in the position of having to teach that to anyone. So the reality is that header units actually give us very, very little. Like it's shockingly little. The alternative is you can either work with the library maintainer to provide a wrapper module, and all the code that you need is literally that. You just do like global module fragment, include header, export module my library, export namespace my library, using things. That's it. That's all you have to do. That's even automatically generatable. Like you can just say like, build system, generate me a wrapper module for these headers. And here's how you're going to compile it, right? And again, you don't need the owner of the library to do it. Let's say curl. Let's say everyone wants to use curl. Someone just creates like C++ module curl wrapping and reuse that. It's fine. Like there's not that much. And finally, if you need macros, like pushing macros to a lower level header and then include the header where you need the macros import the modules for the other syntactic things, I have a really hard time seeing like a reasonable cost benefit on us supporting header units over this alternative. So the reality is that the specification came from like precompiled headers, Clang header modules. It was a very tumultuous process in getting it into the standard. It moved along like very far from like that initial seed idea, like let's just get precompiled headers standardized. And it's unclear right now if we do like go all the way to get this implemented, if we're actually going to achieve the original goals that header units had set. So I'm going to do the bold claim of saying that I think we should just drop it. Like literally just remove every reference of header units and importable headers from the standard and move on. Like making the named module ecosystems great is something we know how to do now. We have a plan, and I fail to see what we're missing by just dropping header units.
Hard.
Questions?
No, how do you really feel?
I mean, it has been a very exhausting journey. Like we have been like at least 5 or 6 meetings just spinning wheels and not getting anywhere on how to make header units work. Like I honestly have no idea how we can make it work.
So, having such a tool that creates the linked module wrapper automatically from the includes, that seems like a very nice proposition. Is that actually something that you've tried out in the real world, or is that just an idea at this point?
I haven't implemented it, but I can see the Clang matcher expressions in my head. It's like, it's really easy.
It's kind of what Shelley was talking about in his keynote, right?
Yeah.
Supposing we had that, could we build with modules today? Or slightly rephrasing the question, what would the status of each compiler be?
So we have, well, Kitware has been working with GCC and Clang. There's a pending patch on GCC. There's a pending patch on Clang to get like this sorted out. Once those patches land, and I'm trying to convince Red Hat, for instance, to backport that patch into like the DTS builds that they do and like the GTS builds that they do. CMake will be very close to like dropping the experimental thing. So I think at the end of this year, if you have a project with internal modules, right, that is your own project defines modules, import modules, you don't ship that module anywhere and you don't import module from anywhere, that should be ready for production use by the end of this year. What we don't have is the entire story that I was describing in here, right? This part we don't have. And this, sorry, let me clarify. If you do like a mono repo style build, where like you bring in all your CMake projects into the CMake project, and like CMake can see the targets across like sub-project boundaries, that should work too. But for like open-ended environments like Linux distributions and Bloomberg, we need this to be possible, right? We need the build system to create the list of identifiers and do the dependency scanning once for each of the identifiers that we need. And that, I think, we're still trying to figure out a roadmap with Kitware on how to get that implemented and when.
I'm assuming there's package management involved in there somewhere.
So for right now, when CMake does find library, What I'm proposing is that CMake is going to find that metadata file that lives alongside the library archive and discover the module metadata. But at the same time, like Brad has been working with SG15, like he has been a lot more invested in that than I have. We actually need to push package management and metadata forward. Like we need to be able to have CMake, build-to, Bazel, to ask the system, what are the packages that you have installed? What are the modules that are provided by those packages?
In a language that's not CMake.
Yeah, in a language that's not CMake export files.
So moving slightly away from the everything is a mono-repo approach. If I'm living in a world where everything is built using CMake, could I just put all of this info in the package config file and then have CMake work everything out? Or
Package config is not enough.
is not enough?
Yeah, no. Build-to has some proposals on how to make package config metadata work.
I think he was talking about the CMake.
Yeah, the
not
CMake.
CMake packages.
Yeah, but like CMake doesn't, like there is no convention on how to document in the package config file. Oh, sorry, you mean CMake export files.
Exactly. Yeah, right, exactly.
I think that may actually work before this, because CMake should be able to export the data about the targets. And if you're exporting from CMake and importing from CMake, I think that is more likely to work sooner than this. But only to the extent that your compile command matches the compile command of the other library to make it BMI compatible. If your project that you're depending on adds a flag that makes the BMI incompatible, you're just going to get a compile time error, can't load BMI.
If you're lucky.
Yeah.
When you say ready, we're compiling and building workflows, right? There's still a lot of work in the modular ecosystem around everything else that understands like where the definitions are and things like that, right?
No, what I'm like, so I was trying to delineate specifically if you're using modules only internally to your project and nobody.
As clarified, you said production ready, you meant you could put it in your build system. There are other things to work on in modules, like how do you get clean tidy to run with the compile commands that JSON and things
Yeah. Static analysis is a whole problem right now.
Clean D or whatever.
Yeah, like language server protocol. We have no idea how like this is gonna work
We'll
yet.
need to step up on,
Yeah.
on those problems.
Like the proposal that I have and like Kitware is working on it is to have alongside compile commands.json having a module config.json that dumps the entire module graph with the source file references and local preprocessor arguments. And then from the outside, you can look at the compile commands.json and the module graph and like produce the BMIs that clean tidy will need if you're using GCC.
There is something in CMake that the way we implemented clang tidy to work with ctest and cdash, which essentially rides it along with the compiler. And I think that will work because the compiler is going to ride through the module systems in the correct order of the graph. And if I'm calling clang tidy right next to the compiler each time, I think that will work.
If the clang tidy that you're using matches exactly the clang production compiler that you're using.
Does it do 2 module maps?
No, it's like,
No.
it's because the build plan should be the same
Yeah.
and the module maps should be the same.
But they're like different extensions and stuff, right?
No, it should all be the same. The question is if you're using a different static analysis tool, if you're using a different version of clang tidy, like we roll clang tidy in a different schedule than the compiler itself.
Right.
And a whole different compiler suite.
Yeah,
It's like, so you need BMIs for Clang version whatever, where your build needs them for GCC.
Right.
You don't
It
have,
would have to match the compiler.
yeah,
And that's
so
how
you have to match.
and that's exactly how IDE workflows work.
right.
Like no one's like making their clang D exactly match the clang of their compile, right? They just get
Or
whatever's the VS
even
code
if you're,
installed, right?
if you're using Clang at all.
Right. Well, these days it's really popular to use clang D for language server protocol workflows. It's
Yeah.
But you're still compiling with GCC,
Right.
and Clang D then says, I know how to understand GCC flags, but it's not going to know how to do Or GCC.
Well, the GCC flags will say, go look at this GCM file, and Clint, he's gonna be like, I don't know what a GCM file is.
Yeah, it's a,
Can you just clarify what it is that we are blocked or waiting on for this story to be true? Is it
Time-
implementation or?
It's just implementation.
Just implementation.
The mental model, I'm very confident that we have a mental model that works. So now, if folks want to see CMake move forward faster, I'm sure Kitware will take more money.
Or like contact, like work with your friends at GCC and Clang and
Yeah, there's lots of patches to be written.
file
Yes.
tickets with Microsoft and kindly, nice tickets that are friendly.
Yeah.
And right now, the thing that's holding up the experimental and CMake is GCC. So we're waiting for all 3 major compilers to actually have it, so we can then take that experimental part out of CMake, so make sure there's not any changes.
Okay, I recall there were some papers still suggesting like things to standardize regarding modules somewhat related to package management. Does that fit into this at all, or is that a separate concern?
I mean, I can fit many papers in that description. What more specifically that you're thinking about?
I was under the impression that there was some consideration to like standardize something about BMI formats or some form of like standardization regarding how modules are understood by consumers. Is that not necessary with this?
So this is, I think you're referring to the proposal that Gabriel dos Reis is talking about, which is the IFC format.
Yes.
So the IFC, so there's two answers that I want to give. So the first one is, I think Gabi's proposal is overly optimistic because the format of the AST is not the standard. For instance, when you look at different versions of Clang, the AST changes for the same language version because the Clang developers realize that the AST design they had was not sufficient to encode the language design for that language version. And so I think for us to get something like what Gabi's proposing, we would need to step up the standard up to like a much higher level of semantics for the language than where we are now. And I'm fairly confident nobody wants to do that. The second point is what I said before, which is the performance characteristics of having to import a module file in the interactive compilation or when building a bunch of different files is probably more important than the interoperability aspect. So I think it's very unlikely that the compilers will converge into a common format because that would have necessarily a significant performance impact. Anyone else? All right, I guess that's it then. Thank you.